There are a few more things that we need to talk about when you're setting up your studies. When the book talks about sample size, what they mean are the number of things that we group together. In order for the math to work, you have to have at least 2 things so that you can calculate a range. But 4 is generally the preferred minimum for the size of a group. As our sample size increases, that standard error of means is going to decrease because we're dividing by the square root of n. So as the sample size increases, the control limits narrow, and that means that our control charts will be more sensitive. In order to make bigger samples, either we have to gather data more frequently, which could be more expensive, or we have to wait longer for each sample to be complete, which means it will be longer until we know whether our process is in control or not. If the sample size is greater than 12, then instead of range, we should use the standard deviation, and we'll figure out how to do that in section 7.5. The bottom line is that sample size is a trade-off. We would really like the sample to be as big as possible, except that that makes things more expensive and time-consuming. So there's a give and a take in that. And in general, the equipment, the process rules, or the times may drive our sample size. The frequency for how often we gather data is also a give and a take. So when you're first studying a process, or after you've just made a change, you're going to want to take more samples because you're going to be more worried that things are out of control. But once the process is in control, then you can reduce that sampling frequency. And again, there's a cost and a benefit analysis that drives these choices. Now, the math that we've been using for how to derive the range charts has paid attention to the asymmetry of range. But in the US, often range charts are simplified. They have upper and control limits that are just 3 standard errors away from the mean. In order to see how this difference in calculating the range charts matters, let's look at the constants that the different techniques use. The black box shows the constants that are used when we are paying attention to the asymmetry of the range chart. So you can see the 4 constants that are the multipliers for the upper and lower warning limits and the upper and lower action limits. The red box shows the constants that are used for setting the control limits when we're using standard error and not paying attention to the asymmetry of the range. The boxes at the bottom of the page show the calculations for how the lines are set in each of these techniques. It's important to note that when we use control lines, we can still use them as action and warning limits. And when you do that, the control limits are the action limits, and they're 3 standard errors away from the center line. But you can also put a line 2 standard errors away and use that as a warning limit. As a starting comparison, let's compare how the upper action limits compare for each of these 2 techniques. In the technique that we've been studying, the upper action limit would be d prime of 0.001 times the average range, where in the control limits technique, it would be d4 times the average range. Since the multiplier in the technique we've been studying is bigger, the upper action limit would be further away from the mean in the technique that we've studied than in the technique that is symmetric. That matches the idea that the range would be skewed in that direction. If we look at the multipliers for the lower action limit in these 2 techniques, the one that assumes symmetry, it is smaller, which means that that control limit will be further away from the mean than the one that we've studied where range is not symmetric. So in that case, the range that is not symmetric would be more sensitive. I firmly recommend that you look at this chart pretty seriously and make sure that you understand why the numbers differ in the way that they differ in this chart, paying attention to when you think the range is symmetric versus when you think it is not symmetric. The rules for how you decide when the process is out of control are a little bit different when you use control limits as opposed to warning and action limits. Basically, they care about whether things are 1, 2, or 3 standard errors away from the mean. And so as much as what we've calculated is 3 standard errors away, 2 standard errors away and 1 standard error away matter as well.